All right, guys, your essential question is how do we evaluate a definite integral using properties of definite integrals? Now, notice your vocabulary, indefinite versus definite. So far, all of the integrals that we have been doing have been indefinite in form. In other words, whenever we take the integral of a function with respect to x, then when we take that antiderivative, we've been having to put plus c to represent a constant because we know that if you take the derivative of this, any constant, the derivative of any constant would be 0, so it just goes away. All right, so then that's why we've had to put that c there, but that's what makes it an indefinite integral, because it can be any function plus a constant. So now we're going to be focusing on something called a definite integral and Riemann sums. Now, if you remember from yesterday, what we did was we said that we could approximate the area under a curve by drawing rectangles. And all of those rectangles that we did yesterday had equal width. However, it doesn't always have to be that way. For example, I could, if I have a function, partition the interval up into subintervals, but notice that the width of these rectangles are not the same. So if I wanted to find the area of each one of these rectangles, I'd have to multiply the width of the rectangle times the height of the rectangle, and then add up all of those sums. And that's what this formula is saying, is that if I multiply the width of each rectangle times the height of the rectangle and add up those sums, I'm going to get a good approximation. Now, what would be the best way to get a better approximation? Well, what I could do is obviously put more rectangles in there, but if I do that, I'm going to have to decrease the size of the width of each interval now. So in other words, I want to get these widths smaller. So what would that look like? Well, as you can see, this is a better approximation of the area under the curve, and if you notice, what I did was I decreased the width of that interval of the rectangles. Well, how can I get a better approximation? Again, I'm going to decrease the width of those rectangles, and as you can see, it's a better approximation. So the question is, if I want to get closer and closer to that true exact answer for the area under the curve, what I'm doing is I'm wanting the width of each one of those rectangles to approach 0. I don't want it to equal 0, because as soon as it equals 0, you know that the area is going to automatically be 0. So that's not going to work. So I want it to approach 0. Well, we learned about stuff approaching numbers. That's the concept of a limit.